In this session, uh, we will learn about vibrations. So this is an important topic where you can get at least 4 to 6 marks in this vibration topic in the gate examination. So I'll start with a simple definition of vibration. And because if you look at the vibration, the concepts which are involved in vibration, so it's a wide aspect. So if you look at some of the PG courses, um, MS specializations, so which are entirely based on vibration. So it is not that simple to finish within 2 hours of this lecture. So to get the knowledge, so we will stick to the gate syllabus where you can get a vast knowledge in a short form. So by looking at a different kind of aspects, and we'll focus on the problem-oriented concepts, which are more important than rather going for in theoretical explanations, so which are derivation-wise it's not required, but formula-wise it is sufficient to remember for the examination. So that's the reason why I prefer to stick to the gate syllabus itself to make you understand in a variety of aspects of vibrations. So I'll start with the definition of vibration. So vibration is a periodic motion of small magnitude. So, but for the sake of simplicity, we generally assume that it is a simple harmonic motion of small amplitudes, something like that. So it is generally a periodic motion. So if any object is in free motion, it tends to move up and down or in a periodic motion. That's what we call it as a periodic motion. Or maybe it is excited with the external force and then it start vibrating. So in generally, we won't use this periodic motion, what is a small magnitude, a high magnitude, all these terms. We generally use a vibration. In depth, if you want to understand, so you have to understand what is the motion of any object when it is rest, when it is under excitation. Uh, So those things will be discussing in the vibration concepts. So, so before going further in detail concepts, so I'll start with some of the simple definitions or the important terms or the terminologies involved in the vibrations. So I'll start with what is a period. So it is generally time taken by a motion to repeat itself, and this is generally measured in seconds. And the next definition is cycle. So what is a cycle? Generally, we use these terms in a vibration concept. So what is a period? What is a cycle? What is a frequency? And all these we need to understand first, and then we can go for a different kind of a concepts later. So what is a cycle? It is just a motion that completed during one time period. Okay. So in a time period which is given, so it has to complete that particular motion. So then it is called as one cycle is finished or one cycle is completed. What is the frequency? Frequency is the number of cycles of the motion completed in 1 second. It is the rate. We are calculating how many cycles have been done or completed within 1 second. It is generally expressed in hertz. So that is a unit we prefer to use. And it is equal to 1 cycle per second, or in general we try to give how many cycles within a second that we represent, that is the frequency of any object. So generally we call natural frequency of object forced frequency of the object. So what is the natural frequency of object? So we'll come to that later. So what is the frequency we just understood? It is a one how many cycles per second. Okay, so that is a frequency. So what is the resonance? So you might have heard in the physics, in the engineering basic classes, what is the resonance? When the frequency of external force is same as that of the natural frequency of the system. Every object has its own frequency where without having any excitation, it will vibrate on its own. That is called as a natural frequency of the system. Okay. So if you are excited, or I mean, the object is excited with external force, and then it got some frequency. Obviously, if you are applying some force, it will vibrate. That frequency is equal to the natural frequency. That is, we call it as state of resonance. It is reaching to the state of resonance. And what will cause the resonance? Resonance results in a large amplitude of vibrations, and this may be dangerous for any kind of a mechanical components or any kind of a physical objects when it is under resonance. So that is where we study these kind of vibrations for different kind of objects, different kind of a mechanical systems, where you can understand the system, mechanical system, and what is actually the response of the system when it is undergoing any kind of force or maybe on its own natural vibration. Once you know how this is reacting to the environment, and then you can design such a system which can resist uh, more for these kind of external excitations. So that is the main intention of understanding these concepts, because this is a purely theoretical I'm explaining. But why we need to talk about this vibration is simply like this. So you are understanding the physical behavior of the object when it is undergoing some kind of a cyclic motions or under excitations, and then get the response from the system, and based on the response you will try to use that as an information in the design and development or maybe in the production process to give the resistance forces, or maybe to make the product in a better fashion to withstand all these excitations, or maybe to withstand these kind of vibrations, because it is in reality it is undergoing some kind of a vibration, and you are taking that as a response, and then you are designing a new product in such a way that it has to withstand for these kind of external forces. That is a important thing. So one second. Yeah. So another thing is, what are the different type of vibrations? Okay, so we'll just briefly understand what are the different type of vibration, and then we can directly jump in, because we stick only single degree of freedom for the syllabus at the gate, so we don't talk about much of the other topics, so it will take a lot of time as well as unnecessary things also, right? So what are the different type of vibrations? Free vibrations, forced vibrations, damped vibrations, undamped vibrations, and longitudinal vibrations. And there are other things also, transfer vibrations and torsional vibrations. We'll just talk about, so it's basically what kind of a force and what kind of action it is undergoing. So based on that, these kind of vibrations are divided or classified. What is a free vibration? Elastic vibrations in which there are no friction or external forces after the initial release of the body, that are known as a free or a natural vibrations. What is the meaning? So elastic vibration in which there are no frictional or external forces. Okay, so you are not applying any force and there are no frictional forces. On its own, it is vibrating once it is released from any kind of external constraint. That is generally called natural vibration. So what is a forced vibration? It is simply reverse for the free vibration. So forced vibration generally, a repeated force continuously acts on the system. So if you are continuously applying any kind of a force, so then that particular vibration is called as a force vibration. So in this, the applied force and the independent of this, the independent of their own natural frequency. Okay, so this is a kind of a forced vibration. So you can observe. So what is a free vibration and forced vibration equation? Then you will come to a conclusion that okay. So this is what the parameters are adding in the mathematical equations or maybe algebraic equations. So that is the kind of a explanation. So what is the damped vibration? So when the energy of the vibrating system is gradually dissipated by friction, another resistance of the vibration, generally we call that as a damped vibration. Okay, so energy of the vibration system gradually dissipated by the friction. Okay, so this is the definition you can give as a damped vibration. So what is undamped vibration? When there is no friction or a resistance at all in the system, then it is generally called as an undamped vibration. But generally, if you just look at the real time objects or the component mechanical systems, no friction kind of a mechanical component you cannot see anywhere, but it is just kind of assumption. Okay, so what is the longitudinal vibration? So the shaft, if you just take any shaft, okay, so it is elongated and shortened. It is up and down. It is moving up and down. So what is the result of that? It will give as a tensile and compressive forces. So if that particular component which is under this tensile or compressive stress, because of elongated shortened motions, that particular component is under longitudinal vibrations. So you can name it. So it is based on the motion of the object. So then transfer vibration. So if you are just take a shaft, you just bent it. Okay, what will happen? A tensile and compressive forces due to the bending. Then this is also kind of a transfer vibration. So you are not elongated and shortening, but you are trying to bend it, but still you are getting the tensile and compressive stresses only. And what is the definition we can give for torsional vibration? So when the shaft is twisted or untwisted, maybe both the cases you can just think of. So what kind of stresses will be developed? Torsional shear stresses. Okay, so if you just take a shaft and try to twist it. So I think you might have heard about in mechanics of materials. So torsional shear stresses will be induced. So those kind of vibrations generally called as a torsional vibrations. So we'll see one by one what is a free longitudinal vibration, damped longitudinal vibrations, and at the end, if we have time, then we'll solve some of the problems, or maybe in the next session we try to solve some of the important problems which are uh, regularly given in the examinations. And before that, we just see the what is the single degree of freedom and what is the 2 degree of freedom or maybe multiple degrees of linear system. Why we are calling that as a linear system? We generally deal with the linearity of the mechanical component. Okay, so just look at the degree of freedom. What it is saying, the number of independent coordinates required to describe a system completely. So this is the important parameter you can see here, independent coordinates. What are the independent coordinates in the required expression or a mathematical equation? Based on that, we decide how many degrees of freedom that particular system has. if you look at this particular equation, single DOF linear system. So this is the usual equation. I think in the finite element analysis, finite element method, you I think you uh, come across this equation mx double dot cx dot kx, which is all with respect to time, and then f is also with respect to t. And what is mck? M is mass and c is the damping, k is stiffness, and f is the external force acting on the body. What is x dot x double dot? X is the distance or the displacement, and x dot is the velocity, x double dot is the acceleration. So this is the fundamental equation to represent any kind of a vibration problem, any kind of a motion problem. It's not only vibration problem. Generally, we derive any kind of a system based on this equation. This is the complete equation. So if you have a subcategories, then we'll neglect some of the terms based on the simplicity or maybe based on the assumptions we take, right? So K is the stiffness. I think in FEM, you have seen only this equation. So maybe this Kx is equal to F. Okay, stiffness multiplied with the displacement and what are the forces acting on the system. Why? Because it is the static problem and we are not doing any kind of a dynamic problem. That is where these two terms are negligible. Only we deal with the displacement. If the system is in dynamic, then we deal with the velocity and acceleration. This is the velocity and acceleration. So if the system is at rest or maybe in the static condition, these two terms will be washed out. Okay, we'll see that one by one. It is not that simple to explain these things, uh, but in general, so this is the simplest form of motion of any component. This is generally called as a motion equation. Okay, so if you look at in the single DOF, what is the difference between two DOF and single DOF? Single degrees of freedom and 2 degrees of freedom. If you look at this velocity, acceleration, so this acceleration, velocity, and then displacement. So these are only depending on the one independent coordinate. Okay, but if you look at this 2 degrees of freedom, x1 double dot, x1, and suddenly another independent coordinate come into picture. And in the second equation also, x double dot 2 and kx1 and kx2, and this is also suddenly another independent coordinate appear in this equation. So it is very simple. Any motion equation which have more than one independent variables, that is not come into the category of single DOF. If they have two, then it is called as 2 degrees of freedom of the linear system. If they have multiples, then multiple degrees of freedom for the linear system. Okay, and then we see what is the system response. So it is the behavior characterized by the motion caused by the excitation. And motion caused by the excitation, what kind of excitation we are giving? Let's assume that it is a free response. The response of the system to the initial displacement and the velocities. And if it is a forced response, the response of the system to the externally applied forces. If you look at free response, we are not applying any external force. to respond, to understand the response of the system. Okay, so it is very clear what is the free response, forced response, and what is the single degree of freedom, what is the 2 DOF system. And it is a fundamental thing to understand these basic terminologies before going for the complicated equations or maybe the systems. Now you can see a characteristics of a discrete system. So what is the continuous and discrete system? Continuous is continuous, just it is combined with each and every segment of the system. And discrete is having some kind of a voids, or maybe there is a discontinuity within the system. Okay, so we can define that in general. So the element constituting a discrete mechanical system are generally 3 types. So what are these? So which are the elements which are relating to the forces, to displacement, velocities, and accelerations. We talk about this displacement, velocities, and then accelerations. If you look at this diagram, so Fs is the external force you are applying. What is happening here? Just look at x1 and x2. Okay, so we are defining with this equation. So this entire schematic diagram, we can define this with Fs. What is the Fs? Fs is the external force applied on the spring system, and this is the tensile force you are applying. And what is the response it can give if you are applying the force? That is what we try to mention, right? So if you look at, we only talk about if you are applying some force, we deal with these 3 parameters: displacement, velocity, and acceleration. Because this system is not in motion or in dynamic condition, we generally talk about the displacement. How this is happening, how much it is displaced, it is generally based on the stiffness of the spring. So that is the another material property you have to understand. Whether it is a spring or maybe other material, the stiffness for any material is a constant. Okay, so if you are taking aluminum material and try to pull it, if you are taking a steel material, try to pull it, and the aluminum material has a more elongation than the steel material. It is a general sense because the aluminum has less stiffness than the steel material. Take any standard workpiece. It's not like different scenarios, but take the same scenario for the 2 materials and try to apply the same force for the 2 scenarios, and then try to see how much it is displaced based on the stiffness of the individual material. So that means how much force you are applying on the system is directly proportional to the displacement, right? So if you are taking aluminum material and the steel material, and whatever the material you take, the force you are applying is directly proportional to the displacement. Okay, and if you want to convert that proportionality into the algebraic equation, then it becomes F is equal to, so if you are changing the proportionality to the equation, that is equality, then you have to multiply with a constant. So that constant is nothing but the stiffness of the matrix. So this D can be expressed in terms of what is x2 minus x1. That is the displacement it has happened. Okay, so this is the simple equation. We got it here. And remember, we are only dealing with the displacement because the system is in a condition of static. Okay, so Fs is the elastic force known as restoring force also for the elastic material. Generally, if it is not going beyond the yield point, then it come back. What does it mean? If you are applying a force and then you just removed it, and then within the elastic limit, it will come back. If it is not within the elastic limit, it will not come back. It will undergo a permanent deformation. Okay, so to represent that, we use this equation. This is the general equation. How much force you are applying based on the displacement is also proportionality. And major material property is dependent is the spring stiffness, or any for that matter, any material for that matter, not only spring, it may be any material, but the thing is K is the stiffness of that particular material. So with this particular equation, so we understand how this is actually working, how we are trying to characterize the system based on the applied forces. Then you can see here the damper and relate the force to velocity, and we'll see how this is possible. Okay, now you think of a damper is a viscous damper or maybe a dash shot. So we already seen that damping is generally the energy of the system which is gradually dissipating by a friction or any other resistance. Okay, so with that note, we can understand how this damper is uh, can be placed in the system and what is the role of it. Damper is simply can resist these kind of a forces. Okay, so generally we have different type of dampers. We'll see in later classes what are the different type of classifications for the damping system. And how these are related, you can see the same damping system you can see here. This is the symbol for damping. And in the previous slide, we have seen the symbol for stiffness. We just have taken as a spring for the standard representation. And here, this is the representation for a damper. And how this damping works. So this is a slope C is a viscous damping coefficient, and the units are Newton second per meter. It is also similar. You can see the what is the force you are applying. Fd is the damping force that resists an increase in relative velocity. So we talked about x dot, x double dot. This is the displacement, and this is the velocity, and this is the acceleration. And now in the last slide, we have talked about the displacement when you are applying a pulling force for the spring that matter, and how much it is displaced is directly proportional to the force how much you applied, and F is equal to K into D. And in the similar way, if you come to the damping position and the same force you applied in terms of damping Fd, and Fd is equal to, again you can relate Fd is directly proportional to the x dot. You can just write x dot or maybe v directly, velocity. Fd is directly proportional to the velocity. Okay, and Fd, if you just convert that as an equation, then you can say that it is the delta x dot. Okay, C is the damping constant. This is also a material property. Very simple terms, you can uh, understand the basic equation in a many ways. It is not only uh, one way of understanding. So you can explore in a different ways to understand the basic equation of motion. So that is very important. How you are understanding based on what kind of a explanations. So this is the damper we talked about, and then we talk about the discrete mass. Okay, so the same scenario, you just take you have a mass and you are applying a force Fm, and this particular mass is accelerated at a quantity of x double dot. Then how can you represent that particular system? Okay, again you are relating the force to the acceleration, and this is F is equal to m into x double dot. Again, F is directly proportional to the acceleration. F is equal to the material property as a mass of the system, and then multiplied with the acceleration. So we have broken down this particular system of motion into three categories. So one is the stiffness, another one is the damping, another one is based on the mass. And what are the independent coordinates? These are the independent coordinates. One is acceleration, another one is velocity, and the next one is a displacement. And all these responses we are getting if you are applying F of t. So that is external force versus the response of the system. That is what we have done here. And if you see how we can find out the series problems and the parallel problems. So if you have a two springs connected parallel, two springs connected in series, how to find out the equivalent K value. So what is the meaning of equivalent K value? So you are not taking the individual K values in the system, but you are taking the equivalent stiffness of the system. How we can do that? Fs is equal to the forces, if they are in parallel, the forces can be calculated. Fs is equal to Fs1 plus 2. You are just adding those two forces. And you know what is the definition for Fs? Fs is a k into the distance, difference in the distance. But you are not taking the individual case, you are taking the equivalent stiffness of the system. What is the equivalent stiffness of the system? The same relation goes for case also. K equivalent is equal to K1 plus K2 if they are in parallel. So I assume that you are aware of how the parallel connection and how the series connections work out. Okay, and in generally, if you have a two, then you can directly make out this equation. So this is the general form of equivalent stiffness calculation, and it goes I is equal to 1 to n k with respect to I. So if you have multiple systems connected in parallel or multiple springs connected in parallel, what is the equivalent stiffness? How we find out? It is simply summation of all the stiffnesses. And what is a spring connected in series? Is exactly opposite. You are just taking the equivalent, just adding all the stiffnesses, and forces also you are just trying to add all the forces which you are applying, but that is not the case for the series problems. Fs is equal to k1 x0 minus x1, and Fs is equal to k2 x2 minus x0. What is the meaning of it? If you are taking for the first system, K1, then you are taking the difference between K0, X0 and X1. If you are taking K2, you are taking the difference to find out the distance X2 minus X0. Okay. But in this case, only X1 is the starting point and X2 is the ending point. So you just take the difference of these two. But in this case, it is not the same because these are connected in series. Okay. So X1 in between X0 again X2. Okay. So this term is an extra term. So where you have to understand the distance uh, response from the system. So that is where you get the two equations for this Fs, right? Now Fs is equal to the same equation k equivalent into x2 minus x1. But here we calculate the stiffness using this equation. It is sometimes we can write this as 1 by k1 plus 1 by k2. So this is how you find out the k equivalent of the system. And this is for the only uh, two stiffnesses of the springs which you are observing here. But if it is having a multiple connections, then you can use this generalized equation k equivalent. And if they won't ask you in a simple manner, they can try to give the equivalent. Uh, they ask you to find out what is the equivalent stiffness in a series parallel, and what is the ratio of these two, or maybe what is the forces acting on the parallel and series system. They can ask in, uh, they can play around any kind of a question, parallel and series, to find out Fs or K equivalent, or the ratio of parallel and series, and so on. And what is the distance difference? So it is the basic scenario to understand this, how it is relating to each other is also important. And you have to remember these formulas to find out what is the equivalent stiffness of the system. Now we talk about the vibrations of the system. Before going further, so we'll see what is the first order and second order. We see already, and now we see in a visualized system what is the we have seen only the single DOF and two DOF. We haven't seen the first order and second order for the same single DOF. Okay, so the whole concept we are dealing with a single DOF, one DOF linear system. Okay, please remember this, because we are not having any independent coordinates other than one, right? So this is the only coordinate we see in the equations. Okay, so other than this, if you are finding any extra independent coordinates, then you might have uh, use these two DOF or maybe multiple DOF linear system based mathematical expressions to deal with any kind of a problem. Now you see the differential equations of motion for first order and second order linear systems. So what is the differential equation? In general, what is the integration and what is the differentiation? What is the integration and what is the differentiation? So integration says the past. Differentiation says about the future. Okay. So just look at this first order system, spring damper system. So, so this is the equation. You can observe there is no acceleration point.